Let's take a little bit deeper look into the delays this time. If you recall last time, we set up a pulse that we could send a noise burst into the delay to easily hear what's going on. Let's do a little something different. Let's take off the Z component of the noise burst. So we basically are just going to gate it at a constant unity volume. Obviously you can hear the delay coming in. Now we're using the voice delay. This is where each voice gets its own delay buffer, but we can also use the sum delay. Let's bring up the manual. The sum delay provides a single multi-tap audio delay buffer shared by all voices. Sum delay is the summed aggregate of all voices in one shared delay. Now what does that really mean to us? Listen to the voice delay. Now let's change that to the sum delay. You can hear the delay is quite accentuated and even a little bit distorted. So the main difference, at least that I can hear, because all the parameters of the sum delay are the same as for the voice delay, is that you're going to get a louder delay out of the sum delay. And it's also related to the polyphony that's set. It turns out, talking to Lippold, that the delay is scaled against the polyphony, even if you're only playing one voice, as I'm doing here. Let's bring that down from bass 5 to polyphony 1, and you'll hear now the sum delay is acting much more like the voice delay for a single voice. So the sum delay is going to give you the larger aggregate sound. Now, all very well and good that we're using pulses, but the majority of the time you're not really going to be using pulses with delays. You'll be using a continuous input of some sort. So let's give that a shot. Instead of the pulse, let's take that off and take an oscillator. Then we'll set it to a more sawtooth-like sound. And let's create a formula that's only going to give me, say, Z going to 0.5 instead of Z going to unity. I don't want to send in the full amount here. So let's send that to the main outputs, and we'll also send it in to the delay. And the delay, of course, will come out on C. I don't need A here anymore. So now I should get my oscillator followed by the delay, which will track the oscillator's motion. That's what I expect. And if I continuously play, that delay will follow me around. All right, let's see what the difference might be with just a voice delay. On bass 1, they're very similar, but let's go up to, say, bass 5 now. Let's play a couple voices even. So the voice delay is not overly powerful in the delay, but let's change that to the sum delay now at bass 5. You can hear that the delay is coming out much more strongly and also possibly distorting it at times because it's so loud. So I think that gives you a good idea of when to use the sum delay versus the voice delay. It really seems to me the main use of the sum delay is to get that stronger delay. And by the way, the manual also states that when a wave bank or manipulator with a spectral set is in use in bank A or bank B, the sum delay will still operate, but using half the normal amount of delay memory. Something similar is stated for the voice delay. When a manipulator with a spectral set is in use in bank A or B, the voice delay will still operate using half the normal amount of delay memory. So the actual delay operation can change a little bit if you're going to be using these other banks in that capacity. Now let's look at the third kind of delay, the micro delay. Back to the manual. The micro delay provides 4 single-tap audio delay buffers for each voice. The micro delay is available in Bank C. The outputs of the micro delay's 4 delay buffers are available on tap 1 to tap 4 matrix rows, alternate choices for the sub and AES in matrix rows. The sum of all 4 delay buffer outputs, tap 1 to tap 4, is available on the Bank C matrix row. So, in some sense, the micro delay is a combination of a voice delay and a sum delay. Let's bring up a micro delay. You'll see there are only inputs for T1, T2, T3, and T4 with corresponding delay parameters that you can set. But the output of the micro delay, if you send it to Bank C, is the sum of all the taps, whereas you can also send each individual tap out the corresponding tap output. What will this sound like? Well, let's set it to a rather high value, 400 milliseconds, and we'll send our oscillator in as we did before with the first tap set to the full 400 delay, and we'll only send that out to the C outputs for now. Let's see what that sounds like. Well, the delay is a little bit distorted. Since we're summing, it seems we're getting that same polyphony scaling artifact happening, and what we can do is let's change this to base polyphony 1, and you can hear the copy now. It's much more like the original. Well, let's see what happens if we go to base 5, and there we're kind of distorted again, but now instead of bringing the delay out of the C bank, let's just bring the first tap out. So there's no summing, I'm just bringing out that first tap. I'm still getting that distortion. So that is going to be there regardless of whether you're using the summed output or whether you're using individual taps. If I set this back to base 1 now, I'm back to the more original sound that I'm expecting. This is, I believe, just how the delay operates. So you're going to have to understand how the sound can change a little bit based on polyphony versus a delay setting. Now let's play around a little bit with the micro delay. Because I have 4 separate inputs, what I could do is send 4 different formulas. Let's send each one of these a little bit less. So I have V that's going to 0.5. I'll send the next tap in on U, which is going to 0.3. T, let me set that one to say 0.12, and I'll send S in at an even smaller value, 0.09, say. Those are my inputs. The oscillator's coming in at those values, and what I'll do now is send in a delay that's a little bit different for each one like we did before. The first tap's coming in at the full amount. Let's make the next tap come in at, say, 0.75 of that, and then the next one will come in at 0.5 of that, and the last one will come in at 0.25, as we did in the first video. Now remember, these are going to be played in the fastest to slowest order, so my last tap will actually be the first delay played. Let's see what that sounds like. We'll turn on all the taps, and we're at 400 milliseconds. We should hear a kind of a constant delay going on there. And I do. We can set that higher. You can hear what's going on there with each of those taps. And if I set it low, and I can set it very low to 12.5 milliseconds at the lowest, this will make all the voices more or less come in together. Just make it sound a little fuller. And I could turn on the sum of everything along with that. It gives it a little more volume, a little fuller sound. Let's bring it back to, say, 100 milliseconds. You get the idea. A very useful function that's used quite commonly in the presets that are using waveguide synthesis. Now the last delay is a much different animal. This is the formula delay. Let's bring up an empty preset. We'll set our formula delay, and this allows you to delay 0.45 seconds, 0.9 seconds, for some reason multiples of 0.45 seconds. And what it delays is control signals, not audio input. Let's read the manual on this one. The formula delay provides 4 delay buffers for each voice for delaying control data used in matrix formulas. Typical values to feed through a formula delay might be X, Y, Z, or pedal. The formula delay is available in Bank C. No output from the formula delay appears directly on matrix rows. Instead, the delay buffer outputs are available by selecting buffer 1 to 4 in the W component of formulas. Let's not read any more because this one is likely not going to be used that much, but let's do a little experiment on it. Let's start by just outputting an oscillator. We'll take our oscillator, set it to that more sawtooth-like sound, and we'll use a formula instead of Z. We'll multiply W set to 1 times Z, which in effect is going to be the same thing as using Z, but you'll see why I'm doing it this way. So we'll put our A formula there, and this will just be playing our oscillator. But let's put a formula delay on this now. Here is our input to the first delay buffer. What we'll do here is we'll just use W as the gate, and we'll delay that by the full amount of our delay. The way this works is buffers 1 and 2 are kind of synced together, and buffers 3 and 4 are kind of synced together. But we'll set this to 1 on our first buffer, and we'll set this to say 0.9 seconds. Now when we go to our A formula, in the cons category, select the formula delay option, and then set which one of my 4 buffers I'm going to delay by. So what this will do is take buffer 1, which has been set to our gate, delayed by 0.9 seconds, and apply that to W. So when I press the fingerboard, I should not hear the sound initially, I should hear it after 0.9 seconds. There we go. After that, as long as my finger's on the fingerboard, I'm okay, but every time I want to regate, I'll regate at my delay value. Let's set it to the smallest value. Hit. There's my delay. I think you get the idea here. This can be used with all kinds of W, X, Y, and Z formulas that you want to delay, kind of like applying delays to a control voltage on a Eurorack. Now the manual also states the sample rate of formula delay's delay memory is normally at the formula evaluation rate of 1 kHz, but it can be limited by 2 variables, maximum delay and polyphony. Very long delays or high polyphony may result in reduced sample rate for the delay memory. Consider filtering or slewing the data inputs to formula delay when using long delay times in the delay pop-up menu to avoid aliasing the control signals being delayed through the formula delay. Now we also saw something similar to this in the other delays, where we saw a slight distortion in the sound for higher polyphony values. Perhaps these are all related. For the next video on delays, we'll look at a factory preset that's an example of each of the delay types we talked about.